Oh,
Ah.
Got it.
Okay, so I'm delighted to welcome Jason DeVito from the University of Tennessee at Martin, who will speak on the non-simply connected double-sold conjecture.
Yeah, thank you. And thank you for inviting me to share my work in this virtual seminar. I know this is the virtual seminar on geometry and symmetries and that kind of stuff. This topic's a little bit more topological in nature, but I'm going to try to make it as geometric as I can as we're going through it. So anyway, just to kind of dive right on in, you can see the table of contents on the left of the screen. I don't know why I'm getting these loading bars every time I hit this page over. Anyway, you can see the table of contents on the left of the screen, but just to kind of give you an outline of where we're going to be heading, I want to start by just motivating what problems I care about, and the big conjectures and the big results in the field. And then we'll talk about the definition of double disk bundles, which play a key role in this double sold conjecture, and do some examples. Talk about a generalization of the double sold conjecture, and then talk about some recent results within that. So I guess without further ado, we'll go right on in. So in some sense, my main motivation, the question that I'm always thinking about and tailoring all my research towards, is answering this fundamental question, which has been asked since the idea of Riemannian metrics have been around. Which manifolds admit complete Riemannian metrics of non-negative sectional curvature? And I will often leave out the adjective sectional. For purposes of this talk, curvature is always going to refer to sectional curvature. In terms of non-compact manifolds, the key result here is due to Cheeger and Gromoll from 1972. It's called the Soul theorem, and it gives a fundamental structure result for non-compact complete Riemannian manifolds of non-negative sectional curvature. It says that they're all diffeomorphic to the total space of a vector bundle, and that vector bundle is projects down to a closed Riemannian manifold, which is called the Soul, and that closed Riemannian manifold has non-negative sectional curvature. In fact, they prove a little bit more. This Soul is actually a totally convex subset of your non-compact guy. And there's more to it, but in some sense, what this theorem is asserting is, if you want to understand the non-compact case, you really have two things to understand: the compact case, the closed case, and then for a given closed manifold that has a metric of non-negative sectional curvature, classifying which vector bundles over that example have these kinds of metrics. And I should mention that both of those problems are incredibly difficult. Just to give you an idea for that vector bundle path of how difficult that is, the kind of most famous example of a non-negatively curved manifold would be a sphere. And if you want to ask the question of which vector bundles over spheres admit metrics of non-negative sectional curvature, we only know the answer if the dimension of the sphere is at most 5, and that's a result of Karstengrove and Wolfgang-Ziller. So for higher dimensional spheres, we don't even know the vector bundles over them that admit these kinds of metrics. So that's a really hard problem. But again, for purposes of today, I want to focus on that other sub-problem, which is, okay, so what closed manifolds admit Riemannian metrics of non-negative curvature? And so first, a lot is known. We have several constructions, several building blocks. So the most famous example, apart from maybe spheres, of manifolds that admit metrics of non-negative sectional curvature is compact Lie groups. So every compact Lie group admits a bi-invariant metric, and you can just compute curvature in that setting. And what you find is it's given as a constant times a norm squared of a Lie bracket of left invariant vectors. So it's manifestly non-negative, and this is kind of the prototypical example of a manifold of non-negative sectional curvature. We also have, I skipped ahead there, didn't need to. We also have in 2000 result by Gromoll and Ziller that cohomogeneity 1 manifolds with codimension 2 singular orbits admit metrics of non-negative sectional curvature. So just to explain some of that terminology, the setting here is you have a group acting on a manifold, and we're going to assume that the action is not transitive. It's not the homogeneous case. That's kind of the best case scenario. It's kind of a second best case scenario. A principal orbit has codimension 1. And what that corresponds to, practically speaking, is that your quotient space is either a circle or it's a closed interval. In the case where this base is a circle, you actually, all your orbits are principal. You get a nice fiber bundle structure on the manifold M, and in turn, it's very easy to see that these examples all admit metrics of non-negative sectional curvature. By far, the more interesting case is when you get this interval quotient, then what ends up happening is all of your orbits are principal except for two, the two corresponding to the endpoints of that interval. And if your manifold is simply connected, at least, then those weird orbits have to be singular, actually smaller dimensional. And so if your principal orbit's codimension 1, the kind of best case scenario would be codimension 2. And then in that situation, you get metrics of non-negative sectional curvature. In fact, G-invariant metrics of non-negative sectional curvature. It's also known that if you replace that codimension 2 with anything higher, that there are counterexamples where you can no longer get a G-invariant metric with non-negative sectional curvature. So this codimension 2 is important. Although I guess I could say less than or equal to 2. Anyway, so that's this result. And there are many examples that this applies to, even though it seems quite special. So for example, using this, Grove and Ziller were able to show that all of the exotic 7 spheres, which can be written as S3 bundles over S4, emit metrics of non-negative sectional curvature. And then a generalization of this to quotients of these things has now gotten all the exotic 7 spheres. Anyway, that's cohomogeneity 1 manifolds. The other building block, or one of the other building blocks of examples with non-negative sectional curvature, is you can take the connect sum of 2 crosses. So a cross is a compact rank 1 symmetric space. It just means sphere or projective space. So real, complex, or quaternion projective space, or the Cayley plane. You take 2 of these things and connect them together, and Cheeger endowed that with a metric of non-negative sectional curvature. And then the last building block here is a relatively recent example with Rafael Torres. So he showed that there's a Z2 quotient of S2 cross S2. It's a nonlinear quotient. It's a weird quotient. And he showed that this example can be equipped with a metric of non-negative sectional curvature. So these are your 4 building blocks. And using these 4 building blocks, we have ways of combining them to make new examples. So kind of the most obvious one is you just do a Riemannian product of 2 things of non-negative sectional curvature, and the resulting manifold has a metric like this. So that was kind of obvious. A slightly less obvious one is you can do isometric quotient. So a free isometric quotient. This goes back to O'Neill's work for Riemannian submersions. If you have a Riemannian submersion, curvature can only get bigger. And so if the total space has a metric of non-negative sectional curvature, and you have this quotient, then the base space also has a metric of non-negative sectional curvature. And every known example of a metric with non-negative sectional curvature is built out of combinations of these 4 building blocks using combinations of these 2 operations. Every example is produced by this. Every known example is produced by this. Okay, so that's how you construct a lot of these things. What about obstructions? What are some reasons you can't equip manifolds with metrics of non-negative sectional curvature? So the kind of biggest result here is due to Gromoll, and there's a Betti number bound. I don't know why I put the word theorem there. He's got a Betti number bound. So what I mean by this is if you have a manifold of a closed manifold of non-negative sectional curvature, you can look at its Betti numbers with respect to any field coefficients. And what Gromoll proved is there's an upper bound on that depends only on the dimension and the choice of field. So the point is, like, you have some kind of control. Like if you say pick rational coefficients, there's a bound that only depends on the dimension for the total Betti number of your manifold. So topologically, things of non-negative sectional curvature can't be too complicated. I should mention the bound is there's a very large gap between the bound that Gromoll has proven in the examples we have, and the expectation is that somehow this bound can be lowered dramatically. But we just don't have the examples or the proof to do that yet. Another result of Gromoll a little bit earlier says we also have a bound of number of generators of pi1. Again, this bound is in terms of the dimension of the manifold. There's some other things. You have this a hat genus by Lichnerowicz. So this is actually an obstruction to positive scalar curvature for spin manifolds. And it's not quite an obstruction to non-negative sectional curvature because you could still have flat manifolds, but for non-flat things, this a hat genus provides an obstruction to non-negative sectional curvature. And then we have some other results on the fundamental group, things like from Cheeger and Gromoll, the pi1 is virtually abelian, so it contains a finite index abelian subgroup. And so we have these obstructions. We also have, a couple conjectured obstructions I would like to talk about. One of them is the Bott conjecture, which asserts that a simply connected closed manifold with a metric of non-negative sectional curvature should be rationally elliptic. And one definition of rationally elliptic that I am particularly fond of is you look at the higher homotopy groups of them, pi2, pi3, pi4, etc. Those are all abelian groups, and so you can tensor them with Q. And once you do that, you get a rational vector space. You take all of those and you put them together and compute the dimension, and you want that total dimension to be finite. So you call something rationally elliptic if you get this bound on the rational homotopy groups. There's another way of thinking about rational ellipticity in terms of the loop space of the manifold. The Betty numbers of loop space grow polynomially. So there's an equivalent condition. The rational Betty numbers grow polynomially. And in terms of this conjecture, you can see that being simply connected is a hypothesis here. One reason why you might include that hypothesis is because pi1, of course, can be non-abelian, and then you have to do a lot of work to understand what you even mean by pi1 tensor q. So yeah, we're going to assume simply connected just to avoid that issue entirely. All right, there's another conjecture, the one that's kind of the focus of the talk today. This is due to Karsten Grove. It's called the double Soul conjecture. And what it says is a simply connected closed manifold with a metric of non-negative sectional curvature is a double disk bundle. So I should probably spend quite a bit of time telling you what a double disk bundle is. It's really the focus of the talk. But I do want to point out that that simply connected hypothesis appears here as well, for reasons that are perhaps a little bit less clear, but we will get into it later. Okay, so what in the world is a double disk bundle? Well, what does this terminology mean? So the idea here is we're going to pick two submanifolds, B1, B2, inside of our big manifold. We're going to have disk bundles over those. I usually think about those as the normal bundles of these submanifolds. And then we're going to assume that the boundaries of these disk bundles just happen to be diffeomorphic. And I want to stress here that no one's saying that the rank of these disk bundles, no one's saying that the dimension of the fibers has to be match between the two of them. I'm just the boundaries are closed manifolds. They may or may not be diffeomorphic, and we're going to assume that they are diffeomorphic. So we choose a diffeomorphism, and that allows us to glue these two disk bundles together along the boundary, and the resulting manifold you get is it's called a double disk bundle. It's two disk bundles glued together. The submanifolds B1 and B2 of M are called the souls, kind of an analogy with the soul theorem of Cheeger and Gromoll, and so that's where the double soul conjecture gets its name from. Okay, so just to make sure we're on the same page, when I say disk, what I'm referring to is a usual Euclidean disk in RK. So nothing special about this definition. We're always going to assume that the disk is at least one-dimensional, and the only reason for that is because in dimension 1 and higher, a disk actually has a boundary, and therefore these disk bundles actually have a boundary, and therefore you can ask for the boundaries to be diffeomorphic. If K is 0, the 0 disk has no boundary, and then this whole definition falls apart. And then I also want to point out something that's kind of nice typologically. If you restrict these disk bundle maps to their boundaries, you end up with sphere bundle maps, and that means you can apply things like Gießen sequences and that kind of thing. So there's, in fact, there's a lot of the results in this field are based on interplays between like a Meyer-Torres calculation, which is, I mean, M has this decomposition as two things union together. Like it's perfect for Meyer-Torres, and then you play that off with these Gießen sequence calculations and learn stuff about your manifold. Okay, so that's what a double disk bundle is, just in terms of definition. Let's get some examples under our belt just so we can understand it. So I like this exercise because you can fully classify the closed surfaces that are double disk bundles with I can fit it on one slide, and I think it provides a lot of just ideas of how these double disk bundles work. So what are the closed two manifolds? What are the surfaces which are double disk bundles? Well, if the fiber disks are all dimension 1 or more, that means the base space has to be dimension 1 or less. So the base space has got to be a point or a circle. And then you can just ask, what are all the two disk bundles over a point? Well, it's just a two disk. The total space is a two disk. And you can also ask, what are all of the interval bundles? What are all the D1 one disk bundles over a circle? And up to bundle isomorphism, there are precisely two. You have the trivial bundle, the cylinder, the annulus, and then you also have the Mobius bundle. In this particular instance, you can see that all the boundaries happen to be diffeomorphic to some number of copies of a circle. So the boundaries are diffeomorphic, you can start gluing. Although the cylinder has two boundary components, so if I'm going to use my cylinder as one of my disk bundles, I actually have to pick the cylinder again for the other one, because I want a diffeomorphism between the boundaries, and the cylinder is the only one that has two boundary components. So in terms of like, how can I glue these things together? Well, I can either pick a disk with another disk, and of course, if I glue those together, I get a two-sphere. I can pick a disk and a Mobius band, and if you glue those together, you get a real projective space RP2. I can take a Mobius band and glue it to a Mobius band along the boundary, and there I get a Klein bottle. And then if I use the cylinder case, once you glue one boundary component, all you have is an extra long cylinder. And then when you glue the other boundary component, depending on your choice of gluing map, you can get a 2 torus or a Klein bottle. So the end result here is that which surfaces are double disk bundles? Well, it's precisely the usual for when you care about non-negative sectional curvature. It's a 2-sphere RP2 Klein bottle and 2 torus. In fact, as part of the work we just did, we actually classified all the ways of writing them as double disk bundles. So a 2-sphere can only be written as 2 disks stuck together. The 2 torus can only be written as 2 cylinders stuck together. Klein bottle had 2 different ways, both using the double cylinder picture and also 2 Mobius bands. And RP2 had the one way of doing it. So I don't know, it's a fun little exercise. Just to get some more examples of how these kinds of things can work. If I take 2 copies of the trivial 2-disk bundle over a circle, so each one of those has boundary a 2 torus, and of course the mapping class group of a 2 torus is well known, and there's many non-isotopic homomorphisms, so there's lots of ways to glue. And if you just kind of look at all the different ways of gluing, you can make many different kinds of spaces. So you can get like the usual Clifford torus picture of S3, you can get S2 cross S1, you can get lens spaces like an LPQ where P and Q are relatively prime, and any option for P and Q can arise from this construction. So the point here is, even starting with trivial disk bundles, you have a lot of freedom in the gluing maps, and you can get a huge diversity of topological types and even geometric types. Of course, S3 and lens spaces all admit positively curved constant curvature metrics, but S2 cross S1, of course, does not. On the other end of things, you can write one space in multiple ways, lots of ways, as a double disk bundle. So just another example to keep in mind, if I take the trivial n+1 disk bundle over an M sphere, and I take a trivial m+1 disk bundle over an n sphere, both of those have boundary Sn cross Sm. And if you glue those together via the identity map, it's easy to see you just came up with a description of a sphere. So high dimensional spheres have many ways of breaking them down as double disk bundles. And I didn't put this in a slide, but for example, S2 cross S2 has infinitely many ways of breaking it down as a double disk bundle, where the boundaries of the disk bundles have pairwise distinct homotopy types. So you can often get a manifold in many different ways. Okay. All of these are just starting with disk bundles and gluing. This is not necessarily the most natural way that mathematicians approach double disk bundles. So where would you see a double disk bundle in your own work? How do these things just naturally arise? Well, for my purposes, the main area, the first place I ever saw them is that the cohomogeneity 1 manifolds that I mentioned a moment ago, these are a prime example. So if the base space of your cohomogeneity 1 manifold, if the orbit space is a circle, then you can just take a double disk bundle structure on the circle and pull it back. And so all of those cohomogeneity 1 manifolds have this double disk bundle structure. And then in the case when the orbit space is an interval, the more interesting case, this is a result of Mostert, that using the slice theorem, you can show that a tubular neighborhood of the 2 scalar orbits are your 2 disk bundles that give you the double disk bundle decomposition of the manifold. And the Galaz, Garcia, and Zarre is Mostert's paper had some issues that were corrected by them. So give them credit for that too. All right, so this is for me definitely the primary place where I see double disk bundles just kind of naturally appear. But just to give some more examples, Mendez and Radetzky in 2019, they proved a slice theorem for singular Riemannian foliations. And as a consequence of that, if you have a codimension 1 singular Riemannian foliation where all the leaves are closed at least, then you're looking at a double disk bundle. And then just to throw out some more examples, there's a 94 paper by Grove and Searle, where they studied maximal symmetry ring actions on positively curved manifolds. So what this is referring to is, if you have a positively curved manifold, you can bound the dimension of the largest possible dimension of a torus, which can act isometrically and effectively. The bound is very roughly half the dimension. And then they have a rigidity statement in the equality case when you achieve that bound. And the way they get that rigidity statement is they showed that the manifold actually has a double disk bundle decomposition, and they understood the pieces and the gluing maps, and that was enough to get a full diffeomorphism classification of the equality case. Let's see, what else do we have? So there's fixed point homogeneous actions with non-negative sectional curvature. This is a result of Spindler's PhD thesis. So we're talking about group actions in non-negative sectional curvature that have a fixed point set, and then you're assuming that the isotropy action on the normal space is transitive on the unit sphere, and then you get this double disk bundle structure. And just to throw out a few more examples, I'm not going to go through these in detail, but these things have been popping up for decades now. So like in the Munet result, if you have an isoparametric submanifold, it is the boundary of two of these disk bundles. So yeah, so these things just, they really do appear all over the place. They're also actually used in construction. So there's some fake quaternion projective spaces that have been built using double disk bundle decomposition. So they're actually, like when I started to look through this, I was kind of surprised at how frequently these things come up to not really be a common topic that you just see in isolation. Anyway, so hopefully I convinced you that these things matter. So I want to return to the double soul conjecture. We've already had this on the board. So it asserts that a simply connected closed manifold with a metric of non-net sectional curvature should be a double disk bundle. And we now know what double disk bundle means. And I want to ask, before I ask the question, I want to mention, when I talk about a generalized double soul conjecture, which is really the theme of this talk, we're going to drop the assumption that the manifold be simply connected. And I want to, again, talk about a few things related to this. Number one, why would you ever believe the double soul conjecture is true? And number two, why are we including simply connected as a hypothesis? And why are we dropping it for the generalized one? Like, where does this simply connected enter the picture? All right, so let's answer that first question. Why might you believe the double soul conjecture is true? So certainly one of the motivating ideas behind it was the fact that we already had the soul theorem for non-compact things. And so you just think, okay, if non-compact things are all vector bundles, what's the analogous claim for closed things? And the easiest kind of generalization of that is you just take two vector bundles, look at the disk bundles inside of them, and glue them together. It's kind of a best case scenario. And so that's one kind of motivation for the conjecture. In 72, in another paper, Cheeger showed that if again, in the context of non-negative sectional curvature, if your manifold has a totally geodesic hypersurface with trivial normal bundle, then cutting your manifold along that totally geodesic hypersurface separates it into two pieces, and that totally geodesic thing is the boundary of these disk bundles on each half. That is the double disk bundle decomposition. So we have a way of kind of producing these things geometrically, and that was kind of motivation. So maybe, of course, a general non-negatively curved thing has no totally geodesic submanifolds, but maybe you can perturb the metric a little bit or a lot and still maintain non-negative sectional curvature, and then get this splitting or something. That's kind of hope. And then what's some other evidence? Well, we just have lots of examples that we can go try to verify this on. So as a reminder, there were 4 building blocks of non-negatively curved things, and 3 of them all give things that satisfy the double soul conjecture. So as already mentioned, cohomogeneity 1 manifolds have this double disk bundle structure. What's new in this bullet point is that they're quotients. So a cohomogeneity 1 manifold has a natural group action. If you look at a sub action that happens to act freely, so the quotient's a manifold, then Wilking observed that resulting space also has this double disk bundle decomposition. In Cheeger's construction of the connect sum of compact rank 1 symmetric spaces, well, if you remove a ball from a compact rank 1 symmetric space, which is what you do when you connect sum, if you remove a ball, the resulting manifold is a disk bundle over, so let me make this concrete. If you remove a ball from CPN, what's left is the boundary of the tautological bundle over CPN minus 1. So the connect sum decomposition is a double disk bundle decomposition in this case. And then in Torres's example, the way he actually constructed this manifold was by putting metrics on 2 disk bundles and then gluing them together nicely, and then using some four manifold topology to recognize what quotient he had of S2 cross S2. So 3 out of the 4 building blocks all satisfy the double soul conjecture. And if you take a product of something that satisfies it and anything else, then that will satisfy the double soul conjecture. And then at least for a lot of quotients, they seem to satisfy the double soul conjecture. We'll see why I hedged my bets on that last statement later on. So a lot of examples do satisfy this. It's an analogy with the soul theorem. There's quite a bit of reason to suspect the double soul conjecture is true. What I would like to point out is that everything I just said, I never said the word simply connected anywhere. So all of this is actually evidence for the generalized double soul conjecture, where we drop this simply connected hypothesis. If you assume your manifold is simply connected, the only thing that really changes in this whole conversation is in Cheeger's result, the second bullet point there. In a simply connected manifold, a hypersurface automatically has trivial normal bundle. So you don't have to add that extra assumption. And other than that, everything I just wrote applies identically, simply connected, non-simply connected case. So this just motivates even more. Why are we assuming simply connected in the double soul conjecture? And the original motivation is when Grove proposed the double soul conjecture, he proposed it as a part of a process, a part of a like a roadmap to resolving the bot conjecture. And so his idea is, well, back in the early 80s, he and Steve Halperin had proven that when you have this double disk bundle decomposition, then the manifold itself is rationally elliptic if and only if the boundary of the disk bundles, the shared boundary, is rationally elliptic. And then the idea is maybe you can prove the bot conjecture via induction. For low dimensional manifolds, dimension 1 and 2 of non-negative sectional curvature, you can just verify the bot conjecture because there's just not many examples. Gauss-Bonnet tells you we have the entire list in dimension 2, and you can just check they all satisfy the bot conjecture. And so maybe you could set up some kind of inductive thing. That was kind of the idea here. If I have a manifold and and it has non-negative sectional curvature, the double soul conjecture gives me this double disk bundle. Maybe I can massage the metric or something to make it totally geodesic at the place where we're gluing, and then that gets a metric of non-negative sectional curvature, so it's a double disk bundle. And you just kind of backwards induct down till you hit one of these things where they're rationally elliptic. One kind of issue with everything I just said is even if your manifold itself is simply connected, this boundary of the sphere bundles does not have to be simply connected. So you have to worry a little bit about what the bot conjecture means in that situation. But Grove and Halperin proved that in this situation, while the boundary might not be simply connected, it's at least a nilpotent space, and that's enough to run all of the rational homotopy theory machinery. So it's kind of good enough to keep all of this going. So that was kind of the original motivation for why you might add this adjective of being simply connected, excuse me, to the double soul conjecture, or at least maybe nilpotent spaces. And a much bigger reason why you would add this hypothesis is we actually know the generalized double soul conjecture is false if you don't include some condition on the fundamental group. In fact, when Grove when he gave this conjecture, right after it, he mentions, by the way, the Poincare dodecahedral space is a counterexample if you don't have some condition on the fundamental group. So what the Poincare dodecahedral space is you start with a 3-sphere. You have the binary icosahedral group. This is the pullback of the symmetry group of the icosahedron in R3 back via the double cover SU2 to SO3, and you mod out by that. So this space is kind of famous because it was a counterexample to the Poincare conjecture as Poincare originally formulated it. So originally his conjecture was in dimension 3, an integral homology sphere should be a 3-sphere, and then he found this example, which is an integral homology sphere, but it's not simply connected. And that's how we got the modern formulation of the Poincare conjecture with the assumption that it's simply connected. So relatively famous example. It's kind of an ideal, like in the realm of non-negative curvature, you couldn't ask for a nicer space in a lot of ways. It's homogeneous, it's positively curved, but it does not have a double disk bundle decomposition. So a very good reason to add the condition of being simply connected is because if you don't, then you run into issues. I do want to point out though that previously, this was the only known counterexample in any dimension to this generalization of the double soul conjecture. All right, so I have an entire talk that's based on the generalized double soul conjecture, which I just told you is false. So I think a very obvious question is, why would you study something if you already know it's false? What's going on here? And so one thing I want to point out is, again, there was only one previously known counterexample, and you kind of want to know why. So is that like a fluke of low dimensions? There's just not enough disk bundles and low dimensions to glue to get this thing, or there's some more general constructions? How does it depend on the curvature? I mean, of course, a positively curved thing could be deformed to non-negative sectional curvature, but it can't be deformed to be flat, for example. So how much is the curvature playing a role in this? And the only way to really know the answer is to have many, many more counterexamples at your fingertips. Another main motivation is perhaps some of the techniques that you use to show that these spaces are not double disk bundles will be applicable to the true double soul conjecture. Maybe those techniques will work even if your manifold is simply connected, and then you actually get a counterexample to the true conjecture. And then I hope I've already convinced you that double disk bundles actually arise in lots of other places. They're just kind of important on their own. And so knowing if something's a double disk bundle can be important in related fields. So for example, the way I actually found some of these counterexamples to begin with is I was trying to understand flat quotients of cohomogeneity one. Let me say that sentence again. I was trying to understand flat cohomogeneity one manifolds and their quotients, and trying to see which spaces you could get. And so if you know, all of these things are double disk bundles by Wilking's result. And so if you can show that one of them, you know, some example of a flat manifold is not a double disk bundle, it can't be obtained as a quotient of a cohomogeneity one manifold. So let's move on to some main results. So the main result I would like, there's actually kind of two results I want to share. This is definitely the main result. So the first result is there are infinitely many three-dimensional counterexamples to the generalized double solve conjecture. So Grove's example is one of infinitely many, and it fits in a nice family. It's actually one of precisely three homogeneous examples. So of the infinitely many counterexamples, three of them are homogeneous and the rest are not. Yeah, so the first result is what's going on in 3 dimensions. And then I was wondering, you know, okay, 3 dimensions is great, but maybe again, it's this issue of you just don't have a lot of double disk bundles. Can we get some higher dimensional things? What's going on here? And kind of on the exact opposite end of the non-negative curvature landscape, we have flat manifolds. And so the result here is in arbitrarily large dimensions, we can get closed flat manifolds, which are not double disk bundles. So just to kind of expand on this result a little bit, for the 3-dimensional examples, what I actually did was a complete classification of the closed 3 manifolds with non-negative sectional curvature, which are not double disk bundles. And you go compare with the list of known examples and get this result. And so because I have a complete classification, I can say with confidence that there are exactly 3 homogeneous examples, no more, no less. And just to kind of say this classification out loud, I'm not going to have a slide for this, but if we're talking about non-negative sectional curvature for 3 manifolds from Hamilton's work, those are either covered by a 3 torus, covered by S2 cross S1, or covered by S3. In the first 2 cases, if it's covered by a 3 torus or it's covered by S2 cross S1, we just have a classification of all the possible quotients, and you can go just check them one by one. There's finitely many. They're all double disk bundles. In fact, all of this work had been done prior to my results. So you just go look at the known examples, and they already had previously no double disk bundle decompositions. This leaves the elliptic case, quotients of S3, and there's, you know, where I had to do a little bit of work. So among those, the actual result is a classification of the fundamental groups that arise. As you might guess, when you have this double disk bundle decompositions, say for Van Kampen is easy to apply. And so I can write down fundamental groups. And for 3 manifolds, that's a very, very strong invariant. And so you can just then compare that with lists of known examples and get this result. Okay, so I don't want to spend any more time talking about that result because I really feel like it's kind of unique to low dimensions. We use the fact that everything in low dimensions is classified and just kind of throw lots of classifications at it. To me, the more interesting result here is the flat examples. And so I want to talk about how we could know, like, how do you do this? There's no reasonable way to classify all the pieces that are involved, especially in high dimensions. And so the way I got these flat examples, and I'll go into a lot more detail in a couple of slides, but the way I got these flat examples is first I proved a general obstruction on the level of homology. So if you have an aspherical manifold, aspherical means the universal cover is contractible, and by Cartan-Hadamard, all flat manifolds, in fact, all non-positively curved manifolds are aspherical. So if you have an aspherical manifold and the first homology group is of odd finite order, then I was able to prove that that's an obstruction to admitting a double disk bundle structure. And okay, so you have this obstruction, great, until you get examples that realize this obstruction, you don't have your examples for the theorem. And so there's another step where we actually have to construct flat manifolds that are have H1 of odd finite order. So the kind of key that goes into actually all the results, the 3 manifold result and everything, the key observation is actually not that difficult to prove, kind of a nice result though. So it just talks about how we deal with the case where a disk bundle, we have a disk bundle of rank 1 and a double disk bundle decomposition. So the key observation is if I have a manifold that has a double disk bundle decomposition, so it's 2 disk bundles glued together, and I'm going to assume that the first disk bundle is rank 1. In other words, the fiber is just an interval, 0 to 1. Then the point is we can find a non-trivial double cover of your manifold, which is actually built just using the second double disk bundle. So this 2 here is not a typo. You just use 2 copies of that second one and build this thing. And so just to throw out some corollaries to this, for double disk bundles, if your manifold is simply connected, so it doesn't have any non-trivial double covers, then any double disk bundle decomposition has to have rank 2 or larger double disk bundles in it. This was a result that was known forever for homogeneous one manifolds, and it's not new here, but it's a nice kind of summary of it. If both double disk bundles have rank 1, then once you find this double cover, both the DB2 and the other DB2 are rank 1, so you can find a double cover of that, and you can find a double cover of that, and you can iterate this process. So if they both have rank 1, you have to get infinite fundamental group. In fact, there's a lot more structure there. So this is a nice observation. I just wanted to spend a couple minutes explaining how you might prove this, because I can actually draw pictures here, so it's kind of nice. So a great example to keep in mind, the one I'm going to use to describe this, is we're going to look at RP2 in the hemisphere model. So I'm imagining RP2 as the northern hemisphere of a two-sphere with antipodal points on the equator identified. And we're going to view this as a double disk bundle just by kind of chopping it right here. Let me try that line again, chopping it right here. So we chop it right there and we get two halves. The two halves are, of course, a two disk. And then this space down here is actually a Mobius band. It's a little bit of effort to see that, but this is going backwards from what we did a moment ago when we classified all the surfaces that were double disk bundles. Now the point here is that this bottom bundle, this D1 bundle, it's a D1 goes to a Mobius band, goes down to a circle. If we look at the boundary of this thing, we get an S0 bundle. S0 goes to the boundary, goes to S1, and all an S0 bundle is a double cover. So this, there's like a double cover hiding in this picture, and what we're going to do is pull back this disk bundle along that double cover, and the end result here is we're going to replace this Mobius band by an annulus. And we still have the hemisphere up here, but now we're just going to stick a hemisphere down here. So this is going to double cover our space. You can actually just see the double cover. These parts here just map in the obvious way. And then this was a pullback by a double cover map. So you get a double cover there, and then these all piece together very nicely, and you get this double cover. And then, okay, so this space on the right is not actually a double disk bundle. It's built out of 3 pieces. But now the idea is we're just going to glue these things here together. And when you're gluing a trivial bundle onto this boundary, the result is diffeomorphic to whatever this top guy was. You have to write some stuff down. There's a little bit of details to check, but that's the main idea. So you have this unraveling process where anytime you have rank 1, you can unravel it in this way. So nice result. So how does this key observation help either for the flat manifold case or the 3 manifold case? Well, we'll see it pop up in a second. So going back to the flat case, I mentioned that there's 2 main details to this flat case. The first one is an obstruction. And if you have an aspherical manifold and the first homology has odd order, then what you have is not a double disk bundle. And so I want to talk about the proof of this just fairly briefly. So the idea here is first you establish that for an aspherical manifold, a double disk bundle has to have both disks have to be rank 1. And the idea for this is a lot of topology. I know this is a geometry seminar, so I'll try not to spend too much time on it. But the idea is if one of your disk bundles has rank bigger than 1, you use the key observation from the previous slide to find a double cover where both of them are bigger than 1. And then you pull all of that back to the universal cover, which is contractible by hypothesis. Because you did this double cover process first, you can use Van Kampen to prove that the inclusion of the boundary of these double disk bundles into the big manifold is surjective on pi1, and that gives you enough structure in the universal cover to reach a contradiction. Very briefly, what that gains you is that the universal cover gets a double disk bundle structure, and the boundary has to be connected based on all of this work. And the reason why connected is important is remember that these boundaries are bundled, they're sphere bundles over the soles. And if you want to use the Giesen sequence, the hypothesis, if you want to use Giesen sequence with Z2 coefficients, the hypothesis, the only hypothesis is that the total space has to be connected. And so now you're going to play the Giesen sequence together with the Meyer-Vietoris sequence because you know the universal cover is contractible. You play these 2 things off of each other, and what you can eventually prove is that this boundary of the disk bundles has to have non-trivial Z2 cohomology in arbitrarily high dimensions. And of course, it's a finite dimensional manifold. It can't do this, and so that's how you get rid of the case where rank is bigger than 1 anywhere. Okay, so that tells you aspherical things have to have, if they're double disk bundles, then both double disk bundles have to have rank 1. How do we use that to get an obstruction using this H1? Well, we're just going to use, again, some simple topology here. So as I said from the key observation, once you're in this rank 1 case, you start getting double covers, and double covers are parameterized by the first cohomology of your manifold with Z2 coefficients. The way I like to think about this personally is a double cover is nothing but an S0 bundle, and you just kind of complete that fiber into an interval, and then you end up with a line bundle of your space, and these are parameterized by H1M with Z2 coefficients. So we have this parameterization, and then you just use universal coefficients. If your H1 is odd torsion, then this H1 is trivial, which means there are no non-trivial double covers. And so if you put all this together, if something is aspherical and H1 is odd order and it's a double disk bundle, you get a contradiction. Aspherical means disk bundles are rank 1. H1 of odd order means they're not of rank 1. It's that simple. All right, so we get this obstruction using some fun topology. Oh, I should also mention this result here. If you go back to that Grove-Halpern paper I mentioned, it's hiding in there, but you can just kind of prove it directly in this case pretty straightforwardly. So they have a much more general result that this is a special case of. Okay, so great. So we have an obstruction, but just because you have an obstruction doesn't mean you have examples that realize this obstruction. So then the other half of this is we need to construct some flat manifolds whose first homology is odd, that has the order of the first homology group is odd order. And the simplest example of a group of odd order is the trivial group that has order 1. So we're going to look for flat examples that have H1 being trivial. And the way we're going to find these is actually, I searched on Math Overflow and found a nice argument due to Igor Belogradek, and we're going to follow that. And it's really, we're going to put together some big theorems from various sources and create these examples. So the first big theorem or big pair of theorems, depending on how you want to classify it, is a complete classification of which abstract groups can be realized as pi1 of a flat manifold. So Bierbach proved that if that pi1 of a flat manifold must be torsion free, and it must contain this z to the n as a finite index normal subgroup. And then the Oslander-Carnisci result is the converse of that, that if you have an abstract group that happens to be torsion free and contains this Zn as a finite normal subgroup, then you can realize it as the fundamental group of an n-dimensional flat manifold. So we have this purely algebraic way of recognizing when a group is pi1 of a flat manifold. And so because we're looking for H1 to be 0, we'll see this in a second, we're looking for perfect fundamental groups. Another big result from that Oslander-Carnisci paper is that any finite group actually arises from this quotient. So going back to the previous bullet point, pi contains z to the n as a finite index normal subgroup. So the quotient is a well-defined group. It's a finite group. And the big result here, again, is that any finite group can appear from this process. And the last result we need is actually like a proposition in a textbook. It doesn't have a name. It's apparently not important enough in group theory to have a name, but we have this result here. So if I have a group with a finite index subgroup, and the quotient is perfect, then it turns out that the derived subgroup, the commutator subgroup of pi, is also perfect. It contains z possibly to a different power as a finite index normal subgroup, and this pi mod z to the n is isomorphic to pi prime mod z to the m. By the way, I didn't say it, but this group here, this pi mod z to the n, is called the point group. It's also called the holonomic group because in the context of the flat manifold, it is the holonomic group as a Riemannian manifold. So this gives so this group theory proposition here gives us a way of converting to a perfect group that has the same holonomic, same point group, and the cost is that maybe the dimension has to change in order to make that work. Okay, so these are all the ingredients. Now I can put it all together. So given any perfect finite group, so just think of the alternating group on n letters where n is 5 or greater. So given any finite perfect group, we use the second bullet point, the second Oslander-Carnisci result, to obtain that finite group, that perfect group, as the holonomic of a flat manifold. It gives us this fundamental group pi. But now we use the group theory result to replace pi by pi prime. And pi prime, of course, is a subgroup of pi, so it's torsion free. And it also fits into this exact sequence by the group theory proposition. So pi prime is also pi1 of a flat manifold. So call that flat manifold n sub phi. And then because because pi prime is perfect, the first homology group, which is just the abelianization of the fundamental group, is trivial. So you get these examples. In terms of how do you know you get inflating examples, it seems reasonable to expect. So you're certainly getting different geometric examples. They have different holonomy, but how do you know you're getting, say, different topological examples? Well, you can quote some results by Bieberbach again, or you can just see it directly. Because this group phi is the holonomy, it embeds into On, where n is the dimension of your manifold. And so that means that the dimension of your manifold has to be at least the dimension of the smallest faithful real representation of phi. And so simple representation theory tells us that for the alternating groups, that this dimension, the alternating group on n letters, this dimension is n minus 1. And so you get these bounds. I should mention that there's also a question on math overflow where people try to work out the exact dimension where these kinds of things appear. And it seems to be a hard problem. I was not able to solve it. So for example, for the group A5, the kind of simplest perfect group in some sense, the bound for the dimension of M sub A5 is between 15 and 59. And that's the best anyone can say, to my knowledge, of that. So we know that these dimensions have to, increase arbitrarily, but we don't have good control over that. Or at least let me not project. I don't have good control over that. Maybe someone else can figure this out. All right. So if you put together these two parts, we have this obstruction and inflating examples. Realizing this obstruction, that's where all of these flat manifolds that don't have double disk bundles come from. In the last couple minutes, I just want to mention one other result. Let's get some actual like group theory, some group actions in here, because this is geometry with symmetries. So I want to talk about the biquotient structure on these flat manifolds that are arising in the theorem, in fact, on all flat manifolds, because something interesting happens. This is not like a deep theorem. I just think it's an interesting observation, and it'll have some impact on some classification results in other fields. So I don't think I've said the word biquotient yet. So when I say biquotient, what I'm talking about is starting with a Riemannian homogeneous space. So this is a space where the group of isometries acts transitively. So it has a large isometry group. And so you look for subgroups that happen to act freely. And once you have such a thing, you can take the quotient and of course get a manifold out of that. These things are called biquotients. They are non-negatively curved manifolds. They are given by quotients of compact Lie groups via Riemannian submersions. That's what this next sentence is saying. And so that's how they fit into that paradigm from many slides ago. So another way to think about biquotients is their orbit spaces, G mod U, where U is not a subgroup of G, it's a subgroup of G cross G. And we're thinking about the elements here, which are of course ordered pairs, as telling you how to multiply on the left and how to multiply on the right. So back to Bieberbach's paper, every closed flat manifold is regularly covered by a flat torus. So to say this another way, if I have a closed flat manifold, I can pull back the metric on that to a torus. I get a flat metric on a torus, and that covering is regular, which means that the det group acts isometrically, and the quotient is whatever manifold you started with. And so to say this another way, what Bieberbach proved is that every closed flat manifold is a biquotient. A flat torus is a homogeneous space. We just showed that every flat manifold is a quotient of a homogeneous space by a free isometric action. So there you go. Every closed flat manifold is a biquotient. So they're all biquotients, but the thing I want to show that's interesting about this is that the structure is a little bit, maybe not what you would expect. So the proposition that I want to spend a minute and a half on or so is if I hand you a closed flat manifold that can be written as a biquotient, and I assume something that seems innocuous, that the group is connected, then the manifold I handed you actually had to be a torus. And so to put this result in proper context, if we're talking about connected manifolds and I tell you it's homogeneous, or I tell you it's cohomogeneity 1 under some action of a Lie group, then you can replace that Lie group with the identity component, and the manifold is still homogeneous or cohomogeneity 1. So we do this all the time. Like if you care about connected manifolds, we often just say we're going to assume our groups are connected. And you can get away with that for a lot of purposes. The point of this proposition is when you're doing biquotients, you cannot do that. So this M here is any closed flat manifold. It could be connected, it could be a Klein bottle, for example. And then the result here is that if you're insisting that your groups be connected, then you're just never going to get a Klein bottle ever. And so the reason that I care about this result is I'm very interested in classifying these quotients of cohomogeneity 1 manifolds that have recently been used to equip all exotic 7 spheres with non-sectional curvature. That's a result of Karen, Goethe, and Shankar. So I'm interested in answering like what other manifolds do you get? And kind of a result of all of this is that whoever solves this problem is going to have to consider disconnected Lie groups, which means all of finite group theory enters in the picture and it becomes significantly more complicated. So there are some serious hurdles there. So anyway, so how do you prove this proposition? Like how do we know this result? Well, we're just going to go back to classification work by Bert Totaro from 2002. So he has a paper on just how do you classify biquotients in general, although he makes the assumption that the biquotients are all simply connected, that the M is simply connected. And basically, you just look at his proofs and see that many of them apply in this situation. And the upshot of all of this is that you can simplify, if you have a closed flat manifold, you can simplify G down into the point where G is a torus. And what's important about tori from this perspective is that they're abelian. So you have this, sorry about that, you have this U, which is a subgroup of G cross G, which is telling you how to left and right multiply. But the group's abelian, so like you can just make it all right multiplication if you want, and it's all the same. So in other words, U is naturally a subset of G cross G, but you can kind of push it into 1 cross G. And now you're talking about homogeneous spaces. U is a normal subgroup of G, you got a quotient, it's a torus, and that's it. So we know all the Lie groups that are abelian, they are all tori, and that's where this pops out. Okay, anyway, that is all I wanted to say. I really appreciate your time and attention. Thank you.
Thank you, Jason. It was really a nice talk. Are there questions?
Oh, Jason, I really enjoyed your talk.
Thank you.
So just to mention, I think Gromoll at some point generalized this double conjecture to also on the assumption that the metric is only almost negatively curved instead of non-negatively curved. But I don't know if that's. I think there are no examples which satisfy one and not the other, if I remember right.
Right, and he also did that for the Bach conjecture.
Oh, so that's right. Yeah.
Yes.
Now, so for these biquotients you talked about, or even homogeneous spaces, what is known about which ones admit double disk bundles in general?
There's a survey coming out by David Gonzalez Alvaro and Luis Guijarro, where they established that in the simply connected case, up to dimension 10, all homogeneous spaces are double disk bundles. For biquotients, it's known up to dimension 7. In general, it's wide open. For example, we don't even know if the Lie groups E7 and E8 have this structure. So, I mean, and I've thought about that problem a lot, but if you have, say you get double disk bundle decomposition and you glue and you compute the cohomology and it agrees with E7. Do you have E7? Like, how would you ever answer that question? So you're talking very high dimensional things.
How about E6 and F4?
E6 is cohomogeneity 1. And F4 is a bundle over the Cayley plane. So you can take a double disk bundle structure on the Cayley plane and pull it back.
Okay.
Yeah, and F4 might also be cohomogeneity 1. I don't remember. And that the fact that E6 is cohomogeneity 1 and E7 and E8 are not as a result of Andreas Koras.
I see. I think if I remember right, in a glance at your paper on the archive, you also mentioned prism manifolds. How do they arise in this context?
So in the 3-manifold case, as I mentioned, I can classify exactly what fundamental groups arise for double disk bundles. And then in the elliptic case, the answer is it's a lens space or a particular Z2 quotient of those called a prism manifold. It's actually, if you go back to that key observation I had on unfolding, it's a folding. You start with the lens space and you fold it up and you get these prism manifolds. So I don't know much about prism manifolds in general. I'm not a 3-manifold topologist, but they're the fundamental groups characterize them. And so I just get these fundamental groups and I'm like, hey, it's these things.
Yeah, I learned about them only recently, actually. Very interesting class of manifolds.
I know almost nothing. And if you look at the literature, so they're parameterized by 2 integers, and no one uses those 2 integers to mean the same thing from paper to paper. It's a lot of difficulty meshing up results.
Right. Okay, thank you.
Mm-hmm.
Are there any other questions? Well, if not, thank you again.
Thank you for having me. It's a pleasure.
Me.